Extending transformer context with rotary positional embeddings. How far back can language models actually remember context? As powerful as models like GPT-3 are, they suffer from limited context capacity due to fixed input sequence lengths. But rotary positional embeddings lift this constraint, allowing models to encode sequence order across virtually endless contexts. In this video, I'll explain the issue of context limitations in standard transformers, introduce the idea of rotary positional encodings, discuss how they allow representing long-range sequence position, and demonstrate their impact on tasks requiring global sequence understanding. Let's expand transformer context. Context length depends on model architecture. Most transformers handle 512 to 2048 tokens, with each layer filtering context before passing them on. After several layers of processing, the longest retention may be just 4,000 tokens. This arises from self-attention having quadratic complexity. Computing on every pairwise token interaction becomes infeasible. But for many applications, we need even longer range modeling, like conversations, stories, legal documents, and more that far exceed these lengths. Without the full picture, language understanding suffers. Rotary embeddings provide a computationally efficient way to encode positional information even for sequence lengths of, say, 65,000 tokens or longer. The key insight is rather than track absolute positions, we can encode relative ordering between tokens using angular rotation embeddings. Each token gets assigned a vector representing an angle or rotational transformation. Tokens close together receive similar orientations, while distant tokens have more rotated embeddings. By introducing controlled changes in embedding angles between subsequent tokens, we create a sequence ordering along any desired context length. This works because cosine and dot product operations can recover the relative orientation of any two tokens based on the angular displacement of their embeddings. Position differences manifest as vector geometry. So even with narrow transformer windows, self-attention layers can leverage these learned rotational patterns in the embedding space to estimate long-range positional relevance between tokens. No direct modeling of pairwise interactions needed. This makes it efficient for handling greatly extended contexts. The effect is most prominent in language tasks requiring understanding complete documents like long-form question answering. Here, for example, rotary-equipped models strongly outperform regular transformers in accurately summarizing 20,000 token contexts and drawing coherent inferences. Memory capacity moves from thousands to tens of thousands of tokens. Automated assistants can also hold more conversational context. Analytic systems can model entire reports or papers rather than just paragraphs, and more possibilities open up once we transcend vanilla transformer limitations. Let's visualize token positions using a sequence colored from red to blue. Standard self-attention loses the original ordering after 4,000 steps by just signaling random colors. But even at 20,000 tokens, rotary embeddings retain color transitions indicating sequence positions accurately through angular encodings extending across the full context length. By sidestepping absolute positional modeling and instead relying on relative orientations in a rotation-based embedding space, we enable transformers to encode sequence order over vastly longer contexts than traditionally feasible. Rotary positional embeddings lift intrinsic length limitations of transformer architectures and significantly improve processing of long document understanding tasks requiring global coherence, summaries, and reasoning. Expanding context capacity opens the door to more capable language intelligence. Math ensures it. Now that we've covered the basics, let's go deeper on exactly how these angular embeddings represent positions across long sequences. Each token gets assigned two vector values, corresponding to the sinusoidal and cosinusoidal transformation of the token's index. These twin coordinate embeddings together encode the rotation specific to that position. Adjacent tokens have similar angular offsets, described by the trigonometric identity. That small changes in input angle theta manifest as small cosine and sine changes. This localization makes nearby tokens have high dot products. But well-separated tokens experience compounding angular divergence. Trig functions amplify initial rotations over many steps, ensuring that distant tokens have very different orientation values and near-zero dot products. This emergent angular displacement phenomenon enables modeling relative positioning between any two tokens along the sequence, no matter how far apart. Self-attention layers leverage vector similarities to estimate positional relevance. Beyond the theory, implementing rotary embeddings is straightforward. Simply assigning each token index a sine and cosine vector based on angular frequency hyperparameters controls the embedding space geometry. Setting these as inputs to existing transformer architectures instantly provides sequence order information across arbitrarily long lengths. No need to radically redesign models. When pre-trained on large corpora, rotary-powered transformers exhibit significantly improved reasoning, completion, and summarization over documents with thousands of tokens. Tasks wanting local context focus on inner attention layers, while globally coherent inferences are distilled from outer layers that accumulate evidence from the full sequence space. This provides great flexibility within the same architecture. Rotary embeddings unlock transformers to expand beyond their traditional context capacity limits towards comprehending much longer document narratives and conversations, all while retaining computational efficiency to scale model capacity. By encoding relative token positions through trigonometric vector spaces, we enable rich document-level intelligence within feasible transformer architectures. Rotary embeddings open exciting possibilities, but they have trade-offs to consider as well depending on application needs. The global token ordering can improve coherence, but reduces flexibility to model local token swaps or reordering that may better fit some domains. Encoding only relative positions is also more ambiguous than explicitly tracking each index location. Additional techniques can enhance understanding of absolute boundaries when needed. So while rotary embeddings provide a computational jackpot for long context modeling, traditional input representations or hybrid approaches may suit some niche use cases better. In closing, by representing sequence position information through relative angular offsets, rotary embeddings expand transformers beyond their classic context length constraints. Tasks requiring document-level reasoning are especially augmented. Yet, absolute ordering is not perfectly encoded, so applications very sensitive to token permutations may want localized representations or hybrid approaches. Overall, rotary embeddings increase context capacity drastically with minimal computational overhead, opening exciting avenues for long-form language understanding. The math delivers on the motivation.